pick your feedback so that I will see if there is an area you would want me to go over in chapter 1. And then I will do that briefly. But I'm really trying my best. I'm working very hard to get you, a handout, kind of, so that you can keep it for your life. One day in the future when you want to reference to it, you just go back to it and reference to it. And something that you can always come back to when you need it. So it hasn't been easy, but I'm really trying my best to get this thing out for you. Today, I want us to look at chapter 2, and if time permits us, see if we can start chapter 3. But there are a lot of things we need to do. Chapter 3, DC machines. That is my goal for tonight. Let's see how far we can go. So before we move on, I would just like to pick, any question. If there is any question anyone has, you can kindly let's discuss it. If there is any concerns, you can kindly let's discuss it before we move on. Okay, great. My renewable guys, are they here? I see a
Yes,
lot
sir, we
of
are
you.
here.
Yeah,
Yeah.
you are the ones who just did AI work for me. I know that the AgriE they are cooking AI work for me. I want to be able to me. Scholastic, I would you work in AI and patron from Hawaii. I beg you. When you take the work and it's AI, just don't bring it. In fact, renewable, your work that is AI, the truth is that I'm not going to waste time and look at it, to be honest with you. So all that time all the hard work you took to write it is just useless. I won't mark it. If you want me to mark it, do a clean work and submit it. I don't mark AI. I've told you this several times. I said the American Monte. I said, looks like you want to test my patience. So please, I beg you, the renewable guys, kindly consider resubmitting your first assignment within 2 weeks. 2 weeks is too much. The reason why I'm giving you 2 weeks is that this week too, you'll get another batch, so that's just the only way you guys will learn and be able to pass the exams. Otherwise, most of you will trail the course. And me, I don't gift marks. And that's the thing. That's quite unfortunate. I don't do that. So I really need to help you to be able to pass. So kindly bear with me on that. Okay, good. So today we are going to start chapter 2. Now, when we talk about electrical machines are they use AC and DC, right? And so we really need to discuss the behavior and the properties of AC and DC. Now, let me see if I can share my whiteboard so that we can, let's see if that is possible. Share screen. Okay, so let me please, can you see my screen?
Yes, sir.
So you can
Yes,
just
sir.
react with
Yes,
a
sir.
thumbs up for me so that, yeah, great. I always like to see feedback. So you can always, um, great. I like that. If I don't see the feedback, then it makes me feel like you guys are annoyed or angry. Yes. So let me always get your feedback. All right, great. Let me see if, let me see if coming. There's, okay. Okay, great. Awesome. I hope you can see my whiteboard too.
Yes, sir.
All right, great. Good. So now we are good to go. We can have a lot of fun. So electricity is transmitted on the poles, right, by AC. Then when they come to our house, somebody has remembered his nursery book. Okay, in our house, all the devices, all the electronics we use, all the laptops, everything in the house uses DC. So the question then is this: why do we use DC? DC is what we use. But then why do we still need to get AC if DC is what we use? In fact, our laptops all use DC, all our laptops, all everything, all the electronics, all of them use DC, everything. In fact, devices that use AC are, power based, like the grinding mill, the large machines that are used in the industry. But even on those large machines, they still use DC to build a control circuitry, right? So if that is the case, if DC is what we use to do meaningful work, why do we still need AC, right? That's a very, very, very important question we need to answer. Because let's say there are two kind of voltages that you have. DC goes this way, it never changes value. It's fixed. AC goes this way, it's always like this. So obviously, we can see that between DC here and AC, one can actually do more work than the other because one is fixed, is constant, giving you the same levels of energy. And one, too, is changing. At times it's high, at times it's low. So if that is the case, that means if we really want to do work, we need the DC. But then why do we still use AC? Now in chapter 1, we've addressed this in the fundamentals. In chapter 1, we've seen that DCs cannot be easily amplified. Now, underline the word easily. It doesn't mean that DCs cannot be amplified. DCs can be amplified. But to amplify DC, you need special circuits that are having computer chips in them called power electronic converters to be able to amplify DC voltage. Now, that makes DC a very complex form of energy, but it's also very efficient. But before you can amplify DC, you need to build special computers for it. So it requires power electronics, right? You need to build special computers that will just be amplifying, DC. In fact, that is why in those days, in the olden days, when digital electronics and computers were not so common, it was the ready choice that, okay, if we really want to transmit electricity, then let's use AC because naturally AC is something we can amplify. But DC is not so obvious, we can easily amplify DC. So as I speak with you, all over the world in the advanced countries, they are currently trialing something we call HVDC, high voltage DC, and is predominantly replacing the AC transmission networks. So I think, okay, we are not doing power systems. I could have given you an assignment on this, but for your own curiosity, you can just go and read more about it later on, right? So we are trialing high voltage DC, HVDC in the advanced world so that people can, transfer DC directly. And when it comes, you just step it down. You don't do a lot of rectification. You just send it to people's house and then they can just use it the way it is. In that way, we wouldn't need to be buying a lot of adapters here and there. The world will be very, very simple. So in the advanced world, they are researching on how to do this. In fact, in US and in UK and in Spain, they have several kilometers of high voltage DC transmission network. It's an emerging area of research. And so a lot of money is going there. If you learn a little bit more and you have an interest there, you could easily get a scholarship to go and, especially for the renewable guys, to go and really be on the leading edge of that technology. So, in some few years to come, my guess is that we may, just like how right now AC is the predominant form for transmission, in some few years to come, high voltage DC would be a predominant form for transmission because it's having a lot of advantages that ACs don't have. So it was not possible in those days because those times technology wasn't advanced. But now technology is advanced, so we can easily transmit electricity from one point to another, even though it's DC. Is that right? Now that is what made AC advantageous for power distribution because you can efficiently transform voltage using a transformer. And it's curious to note that a transformer can have an efficiency of 97%. In fact, a transformer at times, some people claim is the most efficient electrical device, right? Most efficient. That's what some people call it. But it's debatable, right? The most efficient electrical machine. Electrical machine. Because it has very high efficiency. An efficiency of 97% is very, very high. I hope we all agree. Then we like AC because you can transmit voltage over a long distance and have very, very little losses, right? And it's just simple and robust, for motor construction. If you can have um, three different voltages helping you to do work in a certain machine, then you can do more work with that same machine than you can when you have just 1 volt doing the same work. I'm talking about multi-phase, for instance, 3-phase motor and 1-phase motor. So the 1-phase motor is just one voltage source doing work. Then 3-phase motors are 3 voltage sources helping you to do meaningful work in a motor. So really um, makes your work output more. You can do more work with the same motor than you could have done if you were using a DC. So on that side, AC is having those advantages there. And these are 3 advantages of AC for power distribution. And this is something I can very easily ask you in the exams. Now, when we talk about AC, what is the characteristics of AC? AC has some characteristics we need to know, right? When we say AC alternating, you see, when you look at this, it looks like the sine wave, right? So that is a sine wave. So an AC wave can be described by a sine function or a cosine function. Now, you know that sine just starts from 0 and comes back to 0, like this. Then cos, the difference between sine and cos is that while sine starts from 0 and come back to 0, cos starts from high, come back to high. Is that right? Okay. Now, what that means is that if I'm to continue the same cos function, just look closely. Let me just continue the same. You see, it's having a similar shape, just like the sinusoidal function, right? Only that their starting points are what makes the difference. So kindly take note of that. Now, the reason why I'm stressing this point is that in some books, in some material at times, instead of you seeing the equation for, instead of you seeing the equation for, instead of you seeing the equation for sinusoidal wave to be Vt is equal to Vm sine 2 pi ft plus phi, they will rather quote it like this: Vm cos 2 pi ft plus phi. In fact, we electrical engineers always prefer the second option because it is what actually makes sense. Now, why do we say that? You just think about electricity. When you start a generator, it does not start from 0. It actually starts from maximum. Then it comes down to 0. So we, electrical engineers and power systems engineers, we always like to use the cosine expression more rather than the sine expression. But for for communication sake and for easy communication with our fellow non-technical electrical engineers, the sine wave looks more simple and it looks more intuitive than the cosine wave. That is why in most of the dictionary, in most of the books you use, in most of the materials that you'll be using, is actually stated as Vm sine 2 pi ft. Please, do we understand?
Yes, Father.
Great, great, great. Charlie, see how the father coming in home. Hey, boys. Okay, good.
Hey,
Awesome.
Roche.
Now let's look at this equation. When we take this equation, there are certain few things we need to talk about. When we say that Vt is equal to Vm sine 2 pi ft plus phi. Now, so the last time I was saying that when we say a certain function is sinusoidal, if you find the sine of 0, it is 0. The sine of 90 is 1. Cos 0 is 1. Sine 90, sorry, cos 90 is 0. Cos 90 is 0. So in fact, that is why these two curves behave this way. Because when angle is 0, sine is 0. But over here, when angle is 0, cos is 1, so maximum. So a sine function or a sine of a function would give you any number that ranges between 0 and 1. That means that sine and cos are ratios. They are simply ratios. Ratios of what? Or another way for ratio is percentages. So when I say it can be any number between 0 and 1, that means that the numbers can be 0, can be like sine 30. And sine 30 is what? What is sine 30? Yes, please, who has the calculator with him?
They have.
Half.
Yeah, so sine 30 is half, 0.5. Right, then sine 45 is what? What will it be?
0.707.
0.707.
0.707. Now, what it means is that so sine 30 is 0.5, which is equal to what? 50%. Is that right? Then sine 45 is 0.707. That means it's equal to 70.7%. Right. So sine and cos are an expression of a percentage. Sine and cos are an expression of a percentage. An expression of a percentage of what? In terms of AC, it's an expression of a percentage of the maximum, Vmax. Please, we understand.
Yes.
Great.
See that point again.
So sine and cos are an expression of a percentage. A percentage of what? A percentage of the Vmax. So see something here. Yes. Someone is giving us feedback. Can he kindly turn off his microphone? Great. Thank you. So in Ghana, our Vmax is 325 volts. What it means is that so we know that the angle, where is it? So we know the equation is Vm sine omega t plus phi. So let's just say all of these is equal to a certain number x. So let's just say that x now you learned this in senior high school that here is 0, half is 180 degrees, and then full is 360 degrees. So let's divide this 180 and we get 90 degrees. Let's divide this and we get 270 degrees. So let's say that we want to find the value when, it is 90, right? When the angle is 90. So all of this angle here, all of this one.
So we can't see what you are writing.
I'm sorry, I'm moving to it. So let's say that all of this is the angle that we are looking for. So over here, when that angle is 90, the equation is going to be 325 sine 90. Is that right? Please, we understand.
Yeah.
And what will we get over there? You get
We're going to get the
325.
same thing.
Great.
325 again.
325. When the angle is at 180, when theta is 180,
0.
we get 0. So
Yeah.
when it's over here, it's 325, here is 0. So let me. So we have it over here. We have it over here. What happens when we have it as 270? When the angle is 270?
Negative 325.
Negative
325.
325. Okay, which is over here. Right, so negative 325. Then what happens when it's 360? It's 0, right? Because you take sine of it and you have 0. Now, we can find all the angles between 0 and then can find all the angles between 0 and 90, and then we will get the point. Is that right? We will get a point that looks something like this. Then we can find all the angles between 90 and 180, and it looks like this. And we can find all the angles between 180 and 270, and it looks like this, and we can find them and it looks like that. Please, we understand. Great. So this is what we call sinusoidal, right? So it means that sine is actually a ratio, a percentage of the maximum voltage. Now, what that means is that no voltage at any point in time can ever exceed the maximum voltage. All the voltage that will ever occur at any point in time would have a maximum of that 325 or 0, or any number between 0 and that 325. Please, we understand. Okay, now, so we have said that what we're actually looking for is the angle. What we're actually looking for, because sine, when we say VM, when we say VT is equal to VM, and you say that VT is equal to VM sine theta, this is what we actually mean. This theta here, usually, it is very, very difficult. So let's say that we've sparked our generator and it's working. When we start our generator and it's working after some time, it will be very difficult for you to know the angle that it is at. It will be very, very difficult. So to make it easy for us, what we do is this. Let's rather express that angle in terms of time. And in doing that, we have this function as the phase, where this one, the phi, we call it phi. Phi is equal to the phase angle. Phase angle. Then this one is the angular speed, angular velocity, right? Or angular speed, angular frequency, angular speed, or frequency, or velocity. And then the t that we have here is actually time. in seconds. So when we say T, what we mean is this: how many seconds have passed since we turned it off? Now, what this equation means is very simple. Don't think too hard about it. It's very, very simple. When we start a generator, its speed is constant because the frequency must be constant. In fact, it's not always true because there are controls that are making sure that the frequency is constant, and we always balance speed and torque to be able to make sure that the frequency is very constant. Now, so if we assume that the frequency of a genset that is rotating or is turning is constant, then what it means is that if you turn it on after a certain number of time or after a certain seconds, a number of seconds, if the speed is constant, then you can be able to tell accurately how much distance have been traveled and convert that to angle because it's just moving around in circle. So if you know how many RPMs or how many distance has been traveled, then you can convert it to angles and then plug it into the equation to see what particular points are you on that curve so that you can know the instantaneous voltage there. Is that right? So this thing here, this equation here, that theta thing is what converts from the time to angle. Please, do we understand? Please, do we understand?
Yes, sir.
Great. So that equation there shouldn't be something that should confuse you. Now, as
sir,
part of our work, yes.
Sir.
Yes.
Please, you said that theta is converting time to angle,
To
right?
angle. Yes.
Is it not speed or?
No. So look at what happens here. That's why we have time there. So this one is angular frequency, right? And angular frequency has a unit of radians per second.
Okay.
And we are multiplying by what? Time, which is in what? Seconds. Plus file, which is in radians. Right? So you see this one cancels that, then we have rad plus rad. Then we get rad.
Okay.
Right. So it's just an intelligent way of converting time to angle so that we can know, if we know the angle, then we can know what is the proportion of the maximum voltage are we having at that very point in time.
Okay.
Please, do we understand?
Yes, sir.
Great. Excellent. Any question before I move on? Any question? So there was one part of your handout that you guys didn't take serious. But I know that I'll bring it in the exam, so I won't tell you. Because there's one part of chapter 1. When I was drafting it, I was like, this question there, I'll bring it. But I know you didn't learn it, so I'm happy you didn't learn it, so that you meet it in the exams. Very, very, very happy. Come again.
You've told us we will go and learn it.
Hey, you will see that part.
Oh, wow.
That part is hidden. It's my favorite. One of my very. Yes, it's a favorite. It's a very favorite secret. So I really like
the lenses there.
No, it's not on the lens. They want me to say it. No. I almost said it. I won't say it. Okay. Now, before we move on, where is the part? Is on what was good? This side, 1.5. Why does a loaded generator require more mechanical torque, more energy input? This part is very, very important, and we'll come back to it in our AC discussion. So take note of that. Now, there are certain equations you need to know. Very, very, very important. But before I move on, let's look at this wave. Now, when you look at this wave, there are certain features that you really need to take note of. The period is the length of one complete cycle, right? So the period is the length of one complete cycle. How long does it take to complete one full cycle? And that's the period, represented by the symbol T. So T here, T, T. Now, there are many ways you can find a period. Either you look at from where it starts to where it ends, or you look at from the peak to this peak, or from the crest to this crest. Now, it will interest you to note that cosine functions look like this. They start and they end here. Then sine functions start here and they end here. So you can see that there is a certain phase difference between these two. There is a phase difference of 90 degrees between sine and cos. So you can so all the time you can see that sine leads cos by 90 degrees, right? So you can quickly, so when I write a function that sine x, right, is the same thing as cos x plus 90. Then the 90 here becomes the phase angle. So when you see phase angle, phase angle, phase angle, that is what it means. There are times that it doesn't really go the way we want it. So we add those phase angles to balance two equations. So these please give me a minute and let me answer this call.
Okay. So it's not that I want to continue. What do you think, guys?
Sure, flow.
So Sam was talking about DC and AC. So for the DC, no. You say it's back. Let him continue.
Thank you very much for stepping in. So when we talk about phase angle, that is what it means. All right. Now, there are certain equations you really need to take note of. Very, very important. Number one, omega. Omega is equal to 2 pi f. In fact, in electrical machines, you really need these equations. You really, really need these equations. Omega is 2 pi f. Then, now, in Ghana, frequency is 50 hertz. You should note this and never forget it. So take note of that. Frequency in Ghana is 50 hertz. Then frequency is equal to 1 over t. This means that period is equal to 1 over f. So from this equation, we can find the period of Ghana's electricity, and that is equal to 1 over 50 hertz. And this should give us 20 milliseconds. That's very fast. So that means that our waveforms travel a full cycle in 20 milliseconds. Please, do we understand? Okay, then another equation you need is the equation on. So you see, we said that omega is equal to 2 pi f. So if we make f the subject, then f is going to be omega over 2 pi. That is also a very, very important equation you need. Another very, very important equation is converting from RPM to rad per second. And omega is always equal to, yes, what's the formula?
2 pi
2 pi
2 pi f
RPM over what?
over
60.
60.
Now, take note of this formula. It's very, 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 very important. Very, very important, and you need it. So this is the first one. This is the second one. This is the third one.
We are not seeing it.
You are not seeing it. Let me zoom in. Do you not see it?
Yeah, sure.
Yeah,
Okay.
would have been nice to have.
I will share the whiteboard with you after the class. So. Then one other equation you need. 4. It is actually 4. Equation 4. Equation 4 is that VRMS for a sinusoidal wave, underline the word sinusoidal, is equal to square root of VM over square root of 2. Underline the word sinusoidal. This equation is correct only if the waveform is sinusoidal. So when you have a triangular waveform, it doesn't apply to it. When you have a square AC, it doesn't apply to it. It only applies when the waveform is only sinusoidal. So this formula doesn't apply to this wave. No, it can't apply to it. Please, we understand.
Sir,
Yes.
so if the question is not mentioned sinusoidal, how do we identify it as one?
Yes, so in Ghana, you can make that assumption that, for electrical machines, we are studying it in the context of Ghana. And we are studying AC in the context of Ghana. So you can make that assumption. In fact, even if I don't mention it, you can mention it in your solution and say that you assume that the AC wave is sinusoidal. Based upon that assumption, then you can proceed and do your maths to show intellectual integrity and to show intellectual rigor. Shows me that you are smart. You know what you're doing. And I always like students like that. In fact, when I'm marking smart people's work, I just give them marks. You see. So you can just do that. Is that right? Now, this is very, very important. So in your objective, I can just ask you, Ghana's great frequency is this. What's the period? And the period is simple. It's 20 milliseconds. Or I wouldn't even tell you Ghana's frequency because you must know it. Anybody who is working and living in Ghana and using electricity as an engineer must know the great parameters of the electrical energy that we are using in Ghana. Now, one thing which is worth stating and very, very, very important is that whenever you measure, you use a voltmeter to measure any voltage. Whenever you see any power rating, all those values represent VRMS. Very, very important. Very, very, very important. And so take note of this. So when I tell you that a motor is rated 230 volts, I may not add an VRMS, but you should know that that value quoted there as its rating is VRMS. You should know it. It's very, very important. And it's very tricky. In the exams, I won't be telling you everything. I'll just tell you that the nameplate rating of the motor is 230. And when you go to the industry, you also be seeing it. You see that the motors, they've written some numbers on it. And when they write it, they don't just write, they'll just write 240 volts, 230 volts. And you need to know that that number that he has written there, 230 volts, he won't add anything to it. You should know that there is a hidden RMS at the bottom. And so that number always represents the VRMS. Please, do we understand? Now, if I give you a VRMS voltage of 240, that means that from VRMS formula is equal to Vmax over square root of 2. Then we can say that Vmax will be equal to VRMS square root of 2. And this is one equation you really need to understand and know, because you'll be needing it and you'll be meeting it in your life as long as you want to work with electrical machines. You really need it. Please, we understand. Hello.
Yes, sir.
Great. You can react so that I know that you are not sleeping, because this is a midnight class. Hey, we electrical machines as okay. Yo, Matirai. This causes
This equation, it seems like we met it somewhere.
You met it in her.
Okay. Now let's move on. So there is one other thing we need to talk about, facial representation, but look, it's not something I'll be going deep into it. Otherwise, you guys you would have so much information to grasp. Yes, someone's hands is up. Please unmute and ask your question.
Mohammed.
Sorry, it's a mistake.
It was not. You want to react.
Okay, great. Now, in electrical machines, devices that connect to electricity, AC electricity, has either a resistance or a reactance. A resistance or reactance. Now, resistors produce resistance, and reactance is produced by capacitors and inductors. So capacitors produce reactance, inductors produce reactance, and resistors produce resistance. Now, the reason why we don't call the reactance of capacitors and inductors resistance is that capacitors do not actually consume current. No, they don't. They are very passive. They store and they give it back. So they react with the circuit. So they do not consume. Resistors actively consume and waste what they've consumed as heat. So they will just swallow that thing and waste it as heat. But capacitors do not. Capacitors will store and they will release it back into the circuit. That is why we call capacitors reactors. Like capacitors and inductors, we call both of them reactors. And so they have a form of resistance, because when they are storing, when they're taking it away from the circuit and storing it, it poses some form of resistance to the circuit. So we call that reactance. Now, reactance is a form of resistance, but it's not a resistance. Take note of that. Reactance is a form of resistance, but it is not resistance. Okay, so to make the difference between reactance and resistance, we represent reactance with the symbol R. Sorry, resistance with the symbol R, then reactance with the symbol X. Now, since both of these are all forms of resistances to current, if we want to find the sum of them, we want to find the conjugate sum of them, the total or the sums of these is called impedance. Impedance, like its name means, a measure of how much we are impeding the flow of electricity, right? And so we represent that one with the letter Z. Now, X, reactance of capacitor is called XC and is given by the formula 1 over 2 pi FC. And the reactance of inductors is given by 2 pi FL. Now, two things are very obvious from these two equations. For capacitors, it's divided by F. And what that means is that the more frequency you have, the lesser the reactance, right? But if your frequency is small, then the resistance is very, very high. That means capacitors have selective behavior according to the frequency of the current or the signal passing through it. In other words, if the signal passing through it is having a frequency of 0, then the resistance that the capacitor would pose to that signal is infinite. Or we can say that capacitors completely block DCs or static signals, signals that are not changing, signals that do not have a frequency. But they pass all signals that are changing and varying. The higher your frequency, the lower the resistance that is faced. This is inverse for the inductor. In the inductor, the higher your frequency, the more difficult it is to pass. But it can also be said for inductors that if you are a low wave, then if there is no signal change, there is no frequency on the signal can pass through an inductor easily without having any problem, without facing any resistance whatsoever. But we say the inverse for capacitors. Please, do we understand? Okay, great. And there is one behavior of capacitors and inductors we need to mention. And we've summarized it by the acronym CIVIL. CIVIL. C for
Sir,
capacitor. Yes.
the XL, what is it?
XL is the reactance of inductors. In electronics and in electricity, we represent inductors with a symbol L. So X, I've already mentioned to you that X stands for reactance. So X sub L means reactance of inductors. Then X sub C is reactance of capacitors. Please, do you understand?
Sure.
Great. Now, this phrase, this acronym is very important. Civil. Civil, when we say civil, what does it mean? It means that for capacitors, so C stands for capacitors. It means that for capacitors, current leads voltage. current. So for capacitors, current leads voltage. Then for inductors, current leads, voltage leads current. Voltage leads current. So the C is the capacitor, the L stands for the inductor, then for capacitor is I leads V, then for the inductor, V leads I. So I, civil. Is that right? Okay. Now we will come back to this. Now let's talk about power in AC circuits, the power triangle. Then we'll talk about, I think this part should be here. I put it in the wrong place. Now, because of the behavior of capacitors and inductors, capacitors and inductors they are like passive elements and they are reacting. In every circuit they are in, they are just reacting. Now they would take energy in one cycle, then they will give it back in the other cycle. So it makes the use of electricity a little bit complicated. It makes it not very straightforward. For instance, if current passes through an inductor or a voltage passes through an inductor, what happens is that when we say that for a capacitor, current leads voltage, what we mean is this. We mean that for a capacitor, current leads voltage, so current comes first, then voltage comes next. Then for an inductor, voltage leads current, so voltage comes first, then current would follow. Now what that means is that the area, you see that we've always said that power is when you multiply current times velocity, voltage. Right? Power is when you multiply current times voltage. But because of the behavior of capacitors, because they react, they introduce a lot of delays. Because voltage and current, for a resistor, it looks like this. For a resistor, both voltage and current, they are the same place. There is no difference between them. They lie in phase. So we say they are in phase. But then for an inductor and for a capacitor, current and voltage are not in phase. Current leads voltage for a capacitor and voltage leads current for an inductor. Now what that means is that the way they store power will not behave exactly the same way resistors would behave. That means that they would waste some power. In fact, they will be consuming the power, but they will waste it because look here, for instance, in this curve here, in the C curve here, if we are calculating the area under the curve for both cycles, you will see that, let me find a good curve and then show it here. This one isn't making good justice to it. Let me just see if I can get this one. and show a very good curve for you to understand. Okay. This semester there, you guys, you almost killed me. The way I will rest this vacation, you guys have really pulled me. You put me in you put me in a towel and you were squeezing me from every side. Adelaide was the one who was leading the team. Adelaide.
And Scholar to his part.
Yeah, Scholar to his part. She was real. They were pulling me left, right, center. They were not having mercy on me. Okay. Let me just include that. It will help make it simple. Okay, good. So we have exactly, this is the guy I'm looking for. This very, very important. Okay, so let me put it here. Okay. Now, so if I'm able to copy all of this to, I don't know if I can paste it here. Okay, good. Awesome. That works. So let's look at something. Let's look at something here. So this is how a resistor looks like. For a resistor, the voltage and the currents, the line in phase. So if I multiply both voltage, power is equal to current times voltage. So if I multiply both of this, we are going to fall somewhere here, like this. But look at what happens when we want to multiply for an inductor. The area under the curve will look smaller. Because over here, when you multiply them, because they are different side of the grid, you actually can't really use that energy to do any kind of work. Right? Similarly, for this one too, the intersection that encloses both of them will look like this. Now, what that means is that the amount of energy that is available for you to do work is very small, right? So all the energy here is something that you can hardly use to do any meaningful work. All that you can use to do a meaningful work is what lies in the intersection for an inductor and a capacitor. So what that means is that there are two kinds of power here. The real power that you can consume, and then the one that's, yes, you actually consume it, but you can't use it to do any work. You can't account for it. You can't show why you consumed it. You can't show why you were using it for. So that means that there are two kinds of power when we come to AC systems because of the reactive elements that we have. There are two kinds of power. We have the real one, the real power. Then we have reactive power. Now, so the real one is represented by P, reactive power is represented by Q. When you find the sum, because all of these are vector quantities, this is a vector. I hope you all know vector. In senior high school, you studied vector. Cannot come and tell me you don't know vector. So when you find the vector sum of these two, then you will get what we call the total power, or the apparent power represented by S. apparent power. Now, S is equal to square root of P squared plus Q squared, because these are vector quantities. Please, do we understand? Okay, great. So at some point in time, my class was 39. Now it's 33. So you see, people are dropping off bit by bit. We'll see the survival of the fittest night. You'll see.
One for that.
Yeah, I'm afraid that people are tired. Myself, I'm very tired, but we need to do this. It's very important. Yeah. So that means that there are two kinds of power, real and reactive. Now, look at where the problem comes in. This is where it becomes a huge problem for us. If you have a motor or you have a machine, you are consuming real power, and the real power is what is giving you meaningful job or meaningful work output. But that same machine is also consuming reactive power. The problem is that this reactive power that same machine is consuming, it is not really contributing to meaningful work in a tangible, measurable way, but you are paying for it. Because when we are charging you the electricity bill, we bill you based on the amount of S you've consumed, not the amount of P, the one that you use to actually do work. So if you have a grinding mill as an agricultural engineer, or you have an solar AC pump as a renewable energy guy, right, where you are deploying it for communities and they're paying for it, what it means is that they are not going to pay for only the P that they use, but they are also paying for the reactive power. The power that is consumed and is wasted, they're also going to pay for it. That means the more you consume, the more you are wasting. Meanwhile, now the curious fact is also this: if you're able to find a very intelligent way, you can reduce how much reactive power you are consuming whilst maintaining your real power or your true power. And when that happens, when Q falls, then S2 will fall. What that means is that the amount of money you pay at the end of the month in terms of electricity bills will also fall. Please, we understand. Great. To distinguish between these three powers, if there are two, then we add to get three. To distinguish between these three powers, the unit for real power is kilowatt. The unit for reactive power is kVAR. The R stands for reactive. Then the total power apparent is kVA. So whenever you go to a machine and you see that they've written on it that this machine is 12 kVA, that value stands for what? The apparent power. We call it apparent because that is what you're paying for. So it appears that is how much you are consuming, but that is what you're paying for. Is that right? So we have P, Q, and S. Now, because I told you that already, I told you that P, Q, and S are all vector quantities. That means they have a magnitude and direction. Now, if we are drawing them on the Pythagoras plane, then what happens is that P is actually on the adjacent side then Q is on the opposite side, then S will be our hypotenuse. Now, like I told you, see something here. We can maintain P and reduce Q. When we maintain P and reduce Q, then what is happening here is that we're able to maintain P. So we are doing the same work. If here is 5K watt, here is 5K watt, but we've reduced Q. So KVR drops and we pay less in utility bills. In fact, this is one of the reasons why most of the machines on our farms consume so much. Kindly give me a few minutes. Just give me a minute. Let me pick this call. Okay, great. Sorry for the interruption. So what it means is that if you have the same power, so you have a grinding mill, the grinding mill can still grind however you put in it without consuming any extra addition, right? So for the same grinding mill that is grinding 10 bags of cassava for you, if you design the system so well and you maintain it so well, you will be paying less. In fact, if at first you were paying 2,000 cedis every day or 2,000 cedis, 10,000 cedis every month for your light bills, you can still be grinding the same 10 bags and you would rather be paying 4,000 Ghana cedis because you have rectified this, you've reduced Q, and so the meter is reading a lower S. And so you're not paying more. In fact, this is one of the reasons why many agricultural, industrial operators, they pay so much in light bills and they don't understand. It's usually because of this skill. Because the skill is not doing any work on your share, but you have to pay for it. Right? And so we need to find ways of reducing kill so that when we reduce kill, then how much we will pull from the meter will also fall because the meter is reading S. So if we reduce kill, then the meter will read a smaller S and we will pay for that smaller S. Please, we understand.
Sir,
Yes, please.
reducing the Q, won't it affect the machine as well?
Not at all, because the kill is needed to be stored inside the coil. So for instance, if you have a motor, right? So motors are having coils in them. Any device that is having a coil in it, right? So it's having a coil in it. So it is inductive. Inductors are coils. Whenever you coil, we take a wire and make it into a coil, you've made an inductor, right? So inductors are coils. So coils are inductors. Now, any device that we use at home that is having coils in it, motors, fans, blenders, whatever, what have you, all those devices that are having coils, are all inductors. Now, this is what happens when you turn them on. This is where the reactive power comes from. When you turn them on, before, you see, we've talked about how motors work. Sorry, we briefly mentioned about the Lenz's law, and we said whenever current flows, there is a magnetic field around it. So when these coils, when you turn them on, they need to consume some current to produce that magnetic field around it so that you can get the motion that you are seeing in the fan and in the motor and something. Now, that energy that is consumed to be stored inside the fan is where the reactive power is coming from. That is what constitutes or contributes to the reactive power. So look at what happens. You are in a factory and we are in Ghana, there is doomsday every day. Hey, no, my renewable guys, where are they? They are asleep.
They are all
Rahman,
gone. They are all gone.
the renewable guys are going to have to mark them all down. Adelaide, where are you?
They are there.
We
Adelaide.
are there.
Hello, Adelaide. Adelaide is asleep. Sook. Sook is asleep. Oh my goodness.
Because we're for Nukrada.
Scholastica, where are you?
Oh.
Oh, this is not good. Okay. So maybe you guys would take them through the class when they wake up. But let's continue because we still have to continue. So when you start the motor, even I've intentionally I'm intentionally speaking slow so you can follow and understand it well. This part is a little bit complicated. It took me many months before I could understand this because I was teaching myself. So it wasn't easy for me. But I want you guys to understand is when you get this thing, a lot of heavy load is lifted off you. So please pay attention and understand as well. So,
Okay.
so when you turn the motor on, what happens is that it needs to charge that coil. Like it needs to store this, it needs to create that magnetic field. If it is a capacitor also stores energy in an electric field. So when you turn it on and there is no energy already stored, it needs to pull that power and store it in a magnetic field. Oh, who is disturbing the class? Someone has hijacked the. So, hello, are we here? Please, are you following?
Yes, sir, we are following.
We can't see it.
Yeah.
We can't see anything again.
Yes, one of you hijacked
Yeah.
my screen. So I'm now correcting it. Okay, great. So now you can see. Can you see my screen now? Okay, good. So the same thing for capacitors. When capacitors too are turned on at first, their charges, there is no charge in them. So they need to store charges there before it starts to work. The same thing for inductors. So what happens? What happens is that energy that is taken and consumed to be stored inside this field is what constitutes the reactive power. Now, look at what we now do. And this is where it gets problematic, especially when you're in Ghana. When you're in Ghana and the grid is erratic, you'll be there, then you start your machine, you're working. So when you start your machine, then you pull all of that energy that it needs. If you have a large motor, you have a 10 kilowatts motor, crushing a lot of cassava and chipping them, you have a large pump, you've designed a large pump for an irrigation site. The moment you turn it on, then what happens is that it pulls all of that large energy and charges. But you were working, so now it has charged. So as long as the device stays on till the time you are working, it has charged and it's staying on, so you don't have a problem. It won't consume any extra unless the device power is off. But unfortunately for us, the grid is not stable. So when you pull all of that, then you are working, then doomsday will come, and the device will go off, and you have to start again, and it needs to recharge. Then you will be so in a day, if you were not having doomsday, like you will charge once, but because of doomsday, you can charge the coils about 3 or 4 times, and all that energy that it needs to store in the coils, it pulls it from the grid, and you pay for it. Now, what if we know that that energy is stored inside the coils? What if we say that, okay, so instead of we storing it inside the coils, and then when we turn the device off, all of that energy goes back, it just goes away, vanishes. Then when we start, we will pull another one. Why don't we add a bank, a capacitor bank or something somewhere, so that when we turn it on and we turn it off, that energy that we stored inside the coil will move into the capacitor bank and restore it, so that when we are starting again, we don't have to pull that one afresh from the grid. When we do that, what happens? We reduce how much we need for kill. We reduce this, because in that case, what we need will be the little ones we need to top up. Because when we store in a capacitor, it doesn't mean that it will be there. Because of resistances and temperature, it will be coming down. So we will need just to be topping up with small amounts of kill. Then the light bill that we are paying will reduce. Please, we understand. Great. This phenomenon that I've described here is what we call power factor correction. Power factor correction. Now, you see that I left the angle. So this angle is what we call the power factor. The larger the angle, the more energy you waste. The smaller the angle, the smaller the energy you waste. So think about the power factor as how much energy are you wasting from what you are consuming? How much of the energy that you are consuming are you wasting? Now, from this right angle triangle, we can say that cos phi is equal to P over S. That means that P is equal to S cos phi. Similarly, Q will be equal to S sin phi. Please, do we understand? Now, if we say S apparent, S is actually equal to, X is actually equal to I RMS times V RMS. Or we know that I RMS is equal to I max over square root of 2 times V max over square root of 2. So this will be equal to I max V max over 2. Please, do we understand? Hello.
Yes, sir.
Yes, please. Sir.
The yes is going down. The yes
Active,
is
active,
the yes is going
active,
down.
active,
Me ka sɛ nyɛ n'anɔpa na mo nso mo pɛ no anwummerɛ nti mo dagu me so a aba abɛtɔ mo class o. Okay,
active.
so
Sir, we
kindly
are
take
not
the.
listening.
Are you sure? Is
We
that
are
scholastic?
you'll
No.
be now about 10 more church.
Listen.
Who is
You'll be now
talking? Why
Casacula.
go
Yeah,
back.
you're telling more or Casacula on Teno. It's all Ben on
Me answer no so.
Vivian.
Vivian. Is it Vivian?
Yes, sir,
Okay.
it's me.
Come again. Did you say Vivian?
Yes, sir.
Oh, okay, Vivian. I need to note your name down. Great.
That's a phone.
Yes, sir.
So yes, someone has raised his hands up. Please ask your question. So these are the three equations you need. The equation for power factor, the equation for real power and reactive power, then the equation for apparent power. Please, do we understand?
Yes,
Now,
sir.
we will take questions on these. We will solve some questions on these. Also, remember that earlier on I have said that S is equal to square root of P squared plus Q squared. Kindly take note of this equation too. It's very, very important. Okay, so we will come back to these. Later on. Now, let's talk about this very important concept, the concept of multi-phase systems. Multi-phase systems. Adams, your hands is up. Do you have a question? Adams. Okay. Adams has run away. Okay, so you're looking at the concept of multi-phase systems as a three-phase system and then a single-phase system. In the industry, in most of the equipment that you're going to use in the industry, they are all three-phase systems. What it means is that three wires bring electricity to the component and then one wire takes it off. So that means there are four wires, right? So we have the four-wire three-phase system. Then we have the three-wire three-phase system. Then we have the two-wire one-phase system. Now, let's understand what each one means. So if we say the four-wire three-phase system, then we have the three-wire three-phase, then we have the two-wire one-phase. What does this mean? What this means is this. You see, at times you go to a certain workshop and then you see four wires on the pole coming to that workshop. Have you observed that thing before?
Yes, sir.
Yes. Whenever you see four wires coming from the pole, that is a three-phase system. What it means is that you see that in our houses, most of the houses that we live in, you only see two wires coming from the pole. Have you observed that?
Yeah.
In the two wire system, you see, one brings the electricity Then the other one takes it back. So we just need 2 wires. One brings it, then the other one takes it back. But in a 3-wire, what is happening here is this. We have 3 bringing the electricity. So we have 3 bringing the electricity. Then 1 takes it back. So that is the 3-phase, the 4-wire 3-phase system. Now, in a 3-wire 3-phase system, in fact, you will not see it regularly unless you go to the industry. It's used in the industrial system. What you have is just 3 wires. And what is happening is that in these 3 wires, they only bring, they do not take back. They only bring, they do not take back. So the 4-wire 3-phase system is called the Y. Why do we call it the Y? Or the star, the Y or the star? We call it the Y or the star because you can draw it like a Y. This one brings, then here is a neutral that takes it back. So when all of this come and take, so this is, let me call this yellow, phase blue, phase green. And then this one will bring it back. So this one is called the Y, the star. Then this side is called the delta. Delta because only 3 is needed. And it looks like so we have Y, B, G. There is no neutral. Please, do we understand? So this one is called the Y, the delta configuration for a 3-phase. Now, hello, are we here?
Yes, sir.
Vivian.
Yes, sir, we're here.
Oh, Vivian, why are you there?
Sorry, day.
I'm here.
Great. Why are you there? I'm so glad. Thank you very much that you've not slept on me. Now, so in the industry,
No, sir.
what happens is that now look at something. So the delta, if you observe it closely, you can see that the star requires 4 wires to bring electricity to your home. But the delta requires only 3 wires. So if you were ECG or even Netco, which one will you use when you are sending power over a long distance? So what the ECG does is that when they are sending power over a long distance, let's say Bui Dam, Akosombo Dam, very far away, when they are bringing the power from very far away, Bui Akosombo to, let's say, Sunyani, they use the 3-wire method. In that way, they will not waste a lot of money to buy more materials. So they use a 3-wire method to bring the power from Akosombo to Sunyani. Then when they bring the power to Sunyani, to distribute it to people in their houses, you can't give them this power when they don't have a way to return it back. You can't do that. So when we bring it all the way from Akosombo to Sunyani, then because people need to find a way of returning back the power so that we close the loop, they send it out in 4 wires. So what I mean is this. Delta is used for transmission. When we say transmission, transmission is when they are bringing the power from we to us. Then when they bring it to us, you see that whenever you go to any location, there are distribution transformers. Have you seen it? They're always on the poles, right? So when they transmit it to us, then so they'll transmit it to us in delta. And if they're distributing it to our homes, they will distribute it in star. So as an agricultural engineer, as a renewable energy engineer, when we are distributing power to your home, we distribute it in star, in Y for you. Now, let's take a house. This house is having only bulbs and then occasionally uses some blender and some fans. That house doesn't need more power to be given to it. Hello?
No, sir.
No, sir.
No.
Sir.
But look at a story building or another house, let's say 4 rooms, 5 rooms. But each of these 4 rooms, they have an AC, independent AC. They are using washing machines, large washing machines. They are using central chillers. They are using cabinet dryers and all of that. Do you think that if we give both of these houses the same 2 wires, it will be efficient for both of them?
No, sir.
No.
No,
That
sir.
is why we have the 3-phase system. In the 3-phase system, we distribute it, we give it to customers that consume large consuming customers. Right? So large consuming customers, we give them the 3-phase. Please, do we understand? Hello?
So it means that when you are given a 3-phase, which is the delta,
Yes.
you have to be given a 3-phase meter too. Oh, that's what
Yes.
like that.
You have to be given a 3-phase meter too, exactly. If they give you a 3-phase and then you are using a 2-phase meter, it won't work, it won't match. Please, do we understand?
Yes, sir.
Great.
Yes,
You
sir.
guys are really smart. I like your class. Mobbing.
Nti ya no di no so ache.
Oh, I really like your
was
class. You
watching.
guys are good.
I was
Class
watching.
in your form.
Me chere mo ade amembre.
Class in your form.
Watching,
Really like that. So
Boys are good.
so look at what happens here. So we say that
Sir.
3-phase, yes.
Someone mentioned 3-phase meter. I don't understand that part.
So there are 2 kinds of meters. We have the 3-phase meter and the 2-phase meter. Right. So in our houses, most of our houses uses the 2-phase system because the loads are not large. Then in some houses so I went to Accra some time ago, one very, very rich agricultural engineer. In fact, he was in the US. and he has built a very nice mansion at near the airport. I'm forgetting the name of the area. There is a residential site near the airport. And when we go to the house, we're doing some repair and maintenance for him. Very small. It's not so big, like so big, but it's wealthy. But that house had chillers. They had central air conditioners, and we were told that he is a rice farmer. So when he cultivates and harvests the rice and it's wet, he dries it. He's having a drying room that uses heaters from the grid. So the guy was consuming so much. Now, if you take all of his loads, you can you can get like about 5 loads, if you put all of his loads together, that one house alone is consuming can supply about 5 different houses of a two-phase system. So that is what we do. Such a user, you don't give him a two-phase meter. And you can't say that you're going to give him more two-phase meters to meter each of them. No. So we build special meters for them, called the three-phase meters. Please, if you understand.
Yes.
Good. Now, on our farm sites, on our buildings, wherever we are, the electrical machines we use are mostly three-phase, especially on the agricultural engineering side, mostly three-phase. Because let's say you want to chip cassava. Cassava is a very hard material, so you want to pound it and chip it. You need a motor that is having a high torque and high strength. And that motor, if you are giving it just two-phase, it can't do the work you want it to do. So most of those motors are three-phase. That is why, as an agricultural engineer and a renewable engineer, you need to understand three-phase devices and how we rate them. That's why you need to understand the star and the delta. So when you see D, the letter D represents delta, and then the letter Y represents star. Now, let's look at some few terminologies associated with the delta and the star. Let's look at some few terminologies. If I give you this, a star and a delta, look at what we have here. When you look at this diagram I'm showing on the whiteboard, you can see that there is a neutral here, and there is one line labeled A. Please, are we following? Good.
Yes, sir. Yes, we are following.
Now, each of these lines are called faces. We call these ones faces. A face.
Is the face as the same as the wires?
Yes, so the face are the same as the wires, exactly. Face. So when you pull one face and then you pull one neutral, then you have one phase voltage. V phase. So when you look at the delta, we can have three V phases here. We can have the one between A and N, then the V phase between B and N, and we can have another phase between C and N. Please, we understand.
Yes, sir.
Okay. Now, when we look at the delta, it's different because in the delta, you don't have any neutral. So what you have there is line to line. It moves from one line to another line. And so we call that line to line or line voltage, VLL or VL for short. And it's a voltage between any two different lines. This one here is V line BC. Then we have the last line between A and AC. Please, do we understand?
Yes, sir.
Okay, great, great.
No,
Now,
sir. No, sir.
no say.
I didn't get the delta.
The down part. So when you look at it, you see this is line C, right over here. So when it is line C, when we're able to pull between A here and C, then you get the VL of AC. Just like what we did for VL of AB, VL of BC. Please, you understand?
Yes, sir.
Good. Now, usually when we are distributing power or we are bringing power to your homes, this is what we do. What we do is that so there is a relationship between line voltage and phase voltage. And is related by the formula VL is equal to square root of 3 times V phase. This formula is very, very, very important. If you don't know this formula, you can't understand ratings on motors. So motors rating, they write it this way. Motors are what you guys use. Your life as agricultural engineers depend on motors. Your life as renewable energy engineers depend on motors. Motors is everything. Without motors, you don't have any engineering. And motors are rated and they use these ratings on them. So you need to take note of that. Line voltage is equal to phase voltage times square root of 3. Now in Ghana here, mind you that I said all of these voltages are low key, they are all RMS. I hope you remember we said that. Low key, all of these voltages are all RMS voltages. So look at what we have here. In Ghana, our phase voltage, in fact, so in the single phase houses, what they do is, you see, in the 3-phase houses, they bring 4 wires. So they give you 3 phases and then they add a neutral. But in the single phase, like I've told you earlier on, we will just pick one of the phase and then we pick the neutral and we bring it to you. Then you use. Right? You just pick one of the neutral and bring it to you and you use. That is why at times when the power goes bad, what you can see is that some parts of the town have light and some parts don't have light. The reason why that happens is that when they are distributing power, they don't put all the 2 phases on only one phase alone. No. So they distribute. They'll say, okay, we've put 10 houses on phase Y. But we have only 4 houses on phase B. So let's put 6 additional houses on phase B so that we can, balance the load. There is something called load balance, and it's very, very important. If you don't balance the load, the system will not be stable. It would shake. It's just like you're putting so much load on one side, and the whole system will come down. That is why in the community they balance the load. These ones are on, so we have 10 houses on phase 1, 10 houses on phase 2, 10 houses on phase 3. Now, at times when there is power instability, certain phases are more affected than other phases. That's why you see that you are in the same area, but some people's lights have gone off and some people's light is still on. And it's all because of the phases. So for a two-phase house, we know that the voltage that goes to the house is 230 volts RMS. That means that V phase in Ghana is 230 volts for a single phase. Right. Now, using this same formula, then VL would be equal to square root of 3 times 230 volts. And what do we have? We have 415 volts. 415 volts. And this 415 volts is the rating or characteristic values for three-phase systems. So whenever you are in the industry or you are going to look out for any machine, and even if they don't tell you that this machine is a three-phase system, and you look at the power rating and they've written on it 415, without you reading anything additionally, you should be able to know that that machine, that number there, comes on only three-phase machines. Please, do we understand? Andrew, Omada. Okay. On
So,
this note,
say, when you go to our normal area,
okay.
so
So you
when you go to our
understand?
They're online.
Wow.
Yes, sir.
We did.
please, in our community, yeah,
You guys have done well.
so in our
Yes,
community,
sir.
light pole it has 4 phases on it, right?
Yes. Yes.
So it's that it's only 3 that is active. One sends feedback to the station.
Exactly. One takes it back. That's the neutral. That line is what we call the neutral.
Okay.
Yeah.
So from the connection from the meter to the pole,
Yeah.
a user or a customer can decide to put on maybe phase 1 and phase 3 or phase 2 or phase 3 or any way.
Yes. That one is not the user that decide, but it's the netco, the distribution company. They are the one that balance the grid. They know how many houses they've put on this phase.
Okay.
That is why the houses that have more phases or they have the 3 phase, they don't really suffer when there is power instability, because if there is power instability on one phase, they have all the other phases too. So they can simply switch their load to the more stable frequency and then they use.
Okay. But say when sometimes
Yes.
in our area when there is light shortage or there is instability of light, we sometimes call some area, electricians, and then they can
Yes.
climb the pole
Yeah.
and they remove one of our wires from a different phase to another phase,
Yes.
and then the light
Yes.
comes.
Yes.
It's that
So
they've destroyed the settings of the ECG guys, or have they interfered in their balancing?
so those people no say ECG for one show more count me bomb no. Because they are really causing a lot of harm to the grid.
Okay.
They're very dangerous. They're really causing a lot of harm to the grid. And yet, another part. But yes, it's because that's to express to you the fact that, and I'm very happy you are bringing this up. When there is power instability, it doesn't affect all the phases. At times, some phases are better off than others. So we can just simply migrate you from that phase you're on to the other one. But what that means is that it makes the new one because you are moving load from the other one because that other one is having power instability because the load on that line is plenty. Then you are moving that load onto the one that is stable. So that one too will be loaded. Then that one too will be unstable. Then you can, jump the whole grid. And this grid, the way the grid works, it can shut down itself. When, these are computers that are managing the grid. Do you think if it was human beings managing the grid, Masanka said that? So computers, and are making decision in milliseconds. So they balance, and it doesn't balance. Then they just turn it off. Because it's better to turn it off than to watch and let the system crash and get destroyed. In fact, if in section 1.5, where I spoke to you about why generators need more mechanical input, that section is very, very important. I don't know why you guys didn't see, say, here they are, a pick a question of free. That section, if what it means is that if there is more demand on the grid, or there is more demand for electricity than what we have available, the system can crash. It can just collapse. The system will just collapse. In fact, the gensets can even break down. The hydro dams can vibrate. So when we went to Bui the last time, we were told that on days like Sundays and on days like Sundays, Sundays people are at home. People don't go to work, and the lava guys are chopping love, and
Active.
other things. People are watching football and betting, and a whole lot of things happen on Sundays. So there is so much demand on the grid. Then the guy was telling us that during those times when you go to the dam, you can see the whole building vibrating because there is so much demand on the grid. And so the whole building is vibrating. And when we climbed to the control room, all the tiles there has removed. Like the vibration has been able to detach the tiles from the floor. So when you were stepping there, it's sending a bisa, so these things are very dangerous. Now, so when the system just detects that there is power instability, automatically it disconnects everyone so that we will protect the entire grid. Because it's better we disconnect than say, these things are very expensive. Akosombo Dam, it took us like 40 years to pay the debt we used to construct it. Bui Dam, the bank loan we went to take to construct Bui Dam, we've not finished paying it. Now, because of some power instability in the MSA, no, we don't watch that to happen. Please, you understand?
Yes,
Yes,
sir.
sir.
Thank you.
Yes, sir.
Good. Yes.
Yes, yes.
So,
Sir.
it means that any anybody you know you do so no.
Oh, Doomson A2. Ebi wa
Where's
nipa
our
na eye. Ebi wa computer na eye.
Okay.
Yeah. So recently,
Sente, omani down one.
most of the time, system na nkasa bit disengage crowd before the nipa na beba bebe. Oh, serious. Oh, very, very serious. In fact,
Yes.
when it comes to renewable crowd, yeah, it's worse. Because with the renewable systems, very fast. Very, very, very fast. So, I don't know. You should need genset be a caribbean or it's just embedded systems, the computers. And these computers are living in microseconds. In fact, some of them are even in nanoseconds. Engineer very, very fast. So the moment something small is out of balance, only a doom be sharp. Than say you be share na jato system no. And a jasu timitum. Ti agroja beto on the AC wa ko so modamba transformer na share. they're still doing the investigation, so we don't really know what caused it. But it can be some of these issues. It will destroy it right now. Her nature is very dangerous. Very, very dangerous. So yeah, so most of the time the computers are the one causing it. When they detect that, when they try to manage and balance the grid, that's a far. Oh, on Zoom for some load to go off before they would turn it back on. So most of the times, no computers in there before the NEPA crab about. Okay, great. I really like the question. I think Vivian seemed to have a question. Vivian, please ask your question. Why?
Any question?
Jose.
Say
Hello?
Bernard, no question. Bernard, no question.
Bernard.
Wow, question.
I said I don't have any question.
Oh, okay.
I have a
All
question.
right, great. Then let's quickly finish chapter 2. The rest is just examples. So I'll leave that one for you. Just go and solve them. Yes.
I have a question.
Yes, let me hear you.
Please, the street lights.
Yes.
So which phase power them?
That's a very brilliant that's a very brilliant question. So, like I've told you before, that the distribution companies do something that we call load balancing. So they put loads in such a way that is balanced. There is an assumption. So you see, in the star format, right? In the star form, when you look at it, voltage is not the same. Voltage on the line is not the same as voltage on the face. So take note of this. Voltage on the line is equal to square root of 3 times voltage on the face. That's for star. For star. But then for star, there is an assumption that current on the line is the same thing as current on the face. So what we mean is that the same current is what is flowing through phase A, phase N, phase B, and phase C. It's the same current that is flowing through them. If we don't make this assumption, we can't solve this problem. As electrical engineers, we will not be able to solve it. That is why we make that assumption. We make that assumption that the currents on each of these phases are the same for delta. So for star circuit, these are the two assumptions we make, or two equations for star. Two equations is that, number one, VL is equal to square root of 3 times VPH. Then IL is equal to IPH. These are the equations for star or Y. Now, what this equation means is that current must flow, the same current must flow on each phase. And that is why we need to balance it. So if we don't balance it, that means that currents on each phase are not the same. So all the solving that we will solve, all the analysis we will do for our design and diagnosis and the planning, everything will be wrong. That is why we do load balancing, so that we can balance every load on this phase, so that our assumptions can be right and we can do our design and our calculations. So if we are balancing load, we don't put all street lights on one load. If we will put all street lights on one load, then it's because we know that if we put it on on that node or that phase, it balances it. It balances that phase with all the other phase. So usually the choice as to whether we are putting all street lights on one phase or all street lights on different phase depends on the net cooperative based on how many customers are distributed on each phase. Please, do we understand? Please, do we get it? Good. All right. So for a star, it looks like this, right? Then for delta is the other way around. So this is star and this is delta. For delta, we say that VL is equal to V phase, but then IL is equal to square root of 3 I phase. So these are two interchanging formulas. And you should know this. In fact, you should really understand this. Now, the formula for calculating power for 3-phase is different from the formula for calculating power for 2-phase. In 2-phase, we say that S in 2-phase, we just say that in 2-phase, we say S is equal to IV. That's for 2-phase. In 3-phase, S is equal to square root of 3 times IL times VL. Now what that means is that P is equal to S cos phi and S is square root of 3 IL VL cos phi. Similarly, Q, which is S sin phi, will be equal to square root of 3 IL VL sin phi. Please, do we understand?
Yes, sir.
Yes, sir.
Okay, great. Yes. Okay, great. So on that note, we've come to the end of chapter 2. Thank you guys for joining. I will be sharing.
Thank
I
you, sir.
really don't want to share this once with you. But yeah. I'll share chapter 2 with you, then you would look at it.
You will mute your phone and cast it. Okay, sir.
Great. So you can just solve all the questions behind it.
Sure, Father.
Great.
Okay, sir. Sure.
Omo pentema da no do si kan okay say o pentema kwada.
Thank you, sir. God bless you.
Yes, sir.
Nani kum